Hey class, this is Juan Ramirez with EE 2715, Circuits 2 Transients. So today we'll cover the source-free parallel RLC circuit, which is part of Chapter 8, Second Order Circuits. This is Section 8.4. So let's take a closer look at a source-free parallel RLC circuit. And we know that because the circuit is parallel, all the components all have the same voltage across them, right? And again, we care about the inductor current and capacitor voltage. And you can tell by inspection that the voltage across all three components is equal to the capacitor voltage. As for initial conditions, we have the initial capacitor voltage we call V0, and we have the initial inductor current, equal to I0. Because the three components here are in parallel, we can do KCL at the node above, and we end up with the following equation. We look at the current leaving the resistor, or entering the resistor, rather. That's equal to little v, the voltage across the resistor, divided by the resistance, plus, now we'll look at the current through the inductor, and that's equal to 1 over L, integral from negative infinity to 0, VL of t dt. And then we'll look at the current through the capacitor, which we know is C dV dt. If we differentiate and simplify in order to get rid of that integral, we end up with the following equation. And we can rewrite this equation in the following way. Sorry. I goofed up. And that equation looks a lot like the second order differential equation for current in a series RLC circuit, right? With the difference being that now it's voltage. So in the same way, we have damping factor, which is alpha, But alpha is now equal to 1 over 2 RC in amperes per second. So it's no longer equal to R over 2L like it is for a series RLC circuit. Keep that in mind. And we have our natural frequency, which is calculated the same way as it was for the series RLC circuit. 1 over square root of LC. Okay, now using Laplace analysis, we can find the characteristic equation. And that characteristic equation looks like this. With roots that look like this. All right. So all this looks a lot like what we learned in section 8.3 with the series RLC circuit. Difference is that this characteristic equation is for the voltage across the parallel RLC and not the current through the series RLC. So again, we have 3 different cases based on the damping factor and the natural frequency. And these different cases will give different responses. If the damping factor is greater than the natural frequency, you have an overdamped response. Roots are real, different, and negative. And for this to be true, the inductance has to be greater than 4 times R squared C. The roots are equal to what we just wrote down. And the solution for the voltage is A1 e to the S1t plus A2 e to the S2t, which looks a lot like the solution for the overdamped current in a series RLC circuit. Now let's take a look at the critically damped case. Which occurs when the damping factor is equal to the natural frequency. And in this case, the roots are real, identical, and negative. The inductance has to be equal to 4 times R squared C for this to be the case. The roots are equal to each other and they're equal to negative alpha. And the solution for the voltage is A1 plus A2t e to the negative alpha t. Again, same type of response as what we saw for the critically damped current in a series RLC circuit. Now let's take a look at the underdamped case. So underdamped means the damping factor is low. It's less than the natural frequency. Right? Damping means that we're quickly slowing down that energy transfer between the inductor and capacitor. Underdamped means we don't have a lot of damping, we have very little resistance slowing that down. That happens when the damping factor is less than the natural frequency. The roots are complex. And also the real parts are negative. In this case, the inductance is less than 4 times R squared times C. Here, again, we look for the damped frequency. And the roots are equal to negative alpha plus or minus J omega D, which is the damped frequency. The voltage is equal to A1 cosine omega dt plus A2 sine omega dt times e to the negative alpha t. That's for the underdamped case. And then the steps that we take in order to solve a parallel RLC circuit problem will essentially be the same steps we took for the series RLC circuit. So let's go ahead and do a few examples. Start off with example 1. Okay, so this is what our circuit looks like. And we're looking for the voltage across the capacitor, which is the same as the voltage across the 1 ohm resistor and the 0.25 Henry inductor. Let me clarify that. Alright, so our first step to find that voltage will be to find the damping factor and natural frequency. Damping factor is equal to 1 over 2 times RC. The R for a parallel RLC circuit has to be a parallel resistance to the inductor and to the capacitor. And this is the resistance that's present after the transition. So here we see a switch that opens at time 0. So after that switch opens, what you have left is the 1 ohm resistor, the 0.25 Henry inductor, and the 1 farad capacitor. So your value for R is 1 ohm. And so we end up with 0.5 nepers per second. For the damping frequency, for the undamped natural frequency, we have 1 over square root of the inductance times the capacitance. And that gives us 2 radians per second. Okay? So it's clear that the damping factor is less than the natural frequency. Therefore, you have an underdamped response. All right. So for the underdamped case, we usually find roots. Really what's important is for us to find the damped frequency. Which is the natural frequency squared minus the damping factor squared, all under the square root. And that's equal to 1.94. If you're really careful, you could also find the roots. In this case, they actually don't really do much for us. But let's do it anyway. So it's negative alpha plus j times omega d and negative alpha minus j omega d. Okay. Now we'll try to find the initial conditions. And now the initial conditions we're looking at are the capacitor voltage right after the transition and the rate of change of the capacitor voltage right after the transition. And we find those in the same way we found them in the last section, as well as in 8.2. So we'll first look at steady state before the transition, because as soon as a transition happens, that instant right after it, the inductor current will remain the same, the capacitor voltage will remain the same. Okay, now we're looking for the initial capacitor voltage, which, because we're looking at steady state, that inductor is replaced with a short circuit and the capacitor is replaced with an open circuit, but you have them in parallel, so the short circuit will create a short across that open circuit and kind of neglect the effects of the open circuit. So the voltage across that open circuit is equal to 0 because there's a short right across it. So by inspection, that capacitor voltage right after the transition is going to be 0. Now, the current through that inductor right after the transition, well, because it's a short, and that short counteracts any effect that the 1 ohm resistor has. The reason being the voltage across a short, an ideal short, is 0. There's no voltage built up on an ideal short circuit. And that means because that short is in parallel with the 1 ohm, that means that there's 0 voltage across the 1 ohm resistance. And if there's no voltage across it, there's no current through it. So all the current through the 5 ohm resistor goes through the short circuit. So To find that current, you do 100 volts divided by 5 ohms. The full 100 volts is across the 5 ohm because there's no voltage anywhere else in the circuit because of that short. And you get 20 amps. Now let's take a look at the circuit right after the transition. Okay, so now we are going to say the voltage across the capacitor is equal to what it was before because it can't change instantaneously. The current through the inductor also can't change instantaneously. Okay. So what could we say here? Well, one thing is, we know what we're looking for is this. The rate of change of the capacitor voltage right after the transition. And to get that, I need the capacitor current divided by the capacitance. To get the capacitor current, I'm going to do KCL at that red node. So at KCL, we'll look at the current through the 1 ohm resistance, which is equal to the capacitor voltage, because they're in parallel, divided by the 1 ohm resistance, plus the current through the inductor, which is I of 0, plus IC, which is what we're trying to solve for. So I separate IC, and we get negative 20 amps, because the voltage across that capacitor is 0 from our previous calculation. So we plug that into the equation down here. So our rate of change of the capacitor voltage is negative 20. And that's all we need for initial conditions. Now let's go ahead and find this capacitor voltage. Let's remember it's underdamped, which means the voltage will look like this. All right. We know our value for the damping factor, alpha, 0.5. We also know our damped frequency, omega d. So now what we're going to do is let's plug in the initial condition for capacitor voltage right after the transition, which we call time 0. Okay, so that'll give us e to the 0, a1 cosine of 0, plus a2 sine of 0. And that's equal to, the initial condition was 0 volts. Okay, so we can solve for A1. And we find out that A1 is equal to 0. Since we know A1 is 0, we could rewrite our voltage equation to be e to the negative 0.5t times A2 sine of 1.94t. The A1 is 0, so it eliminates the cosine term. Now we look at the rate of change of voltage, since that's our other initial condition. So again, we do product rule. So I'll kind of go a little quicker now. And so you should have this here. So now let's plug in our initial condition for the rate of change of capacitor voltage right after that transition, which should be equal to negative 20 according to our initial condition. So let's plug in 0 for values of time. All right. Okay, so this first term goes to 0. And we're left with 1.94A2 equal to negative 20. And we solve for A2, it gives us negative 10.3. And now we have everything we need to substitute into our voltage equation. Negative 10.3 e to the negative 0.5t sine of 1.94t. That's in voltage for time greater than 0. Like this. And that's our answer. Now let's do one more example. Call it example 2. And we're going to look for, again, voltage for time greater than 0. All right. A little different from previous examples, in this case, the switch closes at time 0. Okay. First step again, find the damping factor. For that, we need to know the resistance, inductance, capacitance. Inductance, capacitance is straightforward. There's only one of each of those. There's 2 resistors, but let's look at what happens right after the transition. After the transition, the switch closes. creating a short circuit, which essentially connects the inductor back to the 20 ohm resistor and the capacitor. So if we're taking a look at the circuit at zero, right after zero, it looks like this. And although it looks a little bit funny, that inductor, resistor, and capacitor are all in parallel. Therefore, the resistance used to calculate damping factor is simply 20 ohms. And we do the calculation and get 500 nepers per second. And the natural frequency is 223.6 radians per second. So in this case, the damping factor is greater than the natural frequency, and therefore the response is overdamped. So for the overdamped, we actually do need those roots. So let's find those roots. The first is going to be negative alpha plus square root of alpha minus omega, not squared. Square root of alpha squared minus omega not squared. That gives you negative 53. The second root is negative alpha minus that square root. And you get negative 947. Now let's take a look at the initial conditions. So we'll first look at the circuit before the transition, assuming steady state. Okay, so let's calculate the capacitor voltage. That's the voltage across the 20 ohm resistor. We could use some simple voltage division. And we end up with 16 volts. The inductor current, we'll have to take a, we'll have to remember that the direction of the current is sort of opposite to what we know is actually happening. Because due to the voltage source, you're going to have voltage drops across the resistors such that the current direction is opposite to what the circuit is showing. But assuming the direction shown on the circuit, it's going to be equal to negative 40 volts divided by both the resistors combined in series. And that's equal to negative 0.8 amps. Okay, so now let's take a look at the circuit right after the transition. Alright, and you'll probably notice a trend that with the series RLC circuits, for the initial condition of rate of change of inductor current after transition, we would typically do KVL to find that. For the parallel RLC circuits, when we're looking for the rate of change of capacitor voltage right after the transition, we'll typically do KCL. Okay, so let's do KCL. KCL says the inductor current is I at 0 plus. The resistor current will be the voltage across the resistor, which is also equal to the capacitor voltage, divided by the resistance. And the capacitor current is what we're calling IC and what we're solving for. Alright, and now we solve for the capacitor current. And we end up with 0. And we know that the rate of change of the capacitor voltage with respect to time is equal to the capacitor current divided by capacitance. Therefore, it's 0 because the capacitor current is 0. Okay. So now let's find that voltage. We have an overdamped case, which tells me that the equation for the voltage will be A1 e to the S1t plus A2 e to the S2t. Well, we know S1 and S2. S1 was, I think it was negative 47. Oh, negative 53 and negative 947. Now we want to find A1 and A2. So let's plug in our initial condition for voltage. So from the initial condition, we know the voltage at time 0 is 16 volts. Therefore, A1 plus A2 is equal to 16 volts. That didn't really tell us much, but we have one more initial condition, so let's check that out before we call it quits. So let's do the derivative of the voltage. No need to do product rule or anything crazy here. That's the derivative of the voltage. And now let's plug in our initial condition. So at time 0. And that's equal to 0 because of the initial condition that we calculated earlier. Therefore, we're left with negative 53A1 minus 947A2 equal to 0. Now we have two equations. into unknowns. So we can do some simple algebra. So let's say we take equation 1 and we solve for A1. And we plug that into equation 2. And it looks something like this. And then you do some math. I kind of did it beforehand. So here, heck, let's just do it. We're left with A2 equal to negative 0.95. Then if we go back to this equation here, it says A1 is equal to 16 minus A2, which will give us 16.95. And now we can plug those into our voltage equation. And this is our final answer. Alright, so hopefully those couple of examples were helpful. We probably saw a good amount of similarities between the analysis of the parallel RLC circuit and finding the voltage across it with the analysis of the series RLC circuit and finding the current through it. I encourage you to check out the book, look over a few more examples, practice on your own, and next we will be looking at step response of series and parallel RLC circuits. Thank you.